Lesson 6.6, Scatter Plots and Lines of Fit. First, we want to talk about what is a scatter plot. A scatter plot is a graph of plotted points that show the relationship between two sets of data. When we have two sets of data, that's known as bivariate data because there are two variables. And the scatter plot can help to show if there's a correlation between those two variables or not. We can have a positive correlation in which the dots that we've plotted move in a generally upward position. We can have a negative correlation in which they move in a generally downward correlation. And we can have no correlation at all, which occurs when you have just random scattering and no visible pattern. Positive correlation occurs when both sets of data increase together. For example, as a child ages, they grow taller. So age and height will increase together, up to a certain point, of course. A negative correlation occurs when one set of data increases while the other decreases and vice versa. So as the temperature increases, the amount of water in a puddle decreases. No correlation occurs when the sets of data do not have an effect on one another. So as the number of books written increases, it has no effect whatsoever on the number efficiency. Correlations can be strong or weak. A strong correlation indicates that there's a potentially strong relationship between the sets of data. A weak correlation shows a weak relationship. So here and here we have positive correlations, and here we have negative correlations. But as you can see, the clustered together in more of a linear fashion shows a strong correlation. And here we have a general upward pattern, but you can tell, see, we have a generally upward pattern, but you can tell that they're not clustered together very strong. And so this is a weak correlation. And this is a strong positive. And a weak positive. And here we have a strong negative and a weak negative. You can still see in the weak examples that the generally downward trend continues, but again, the points are not clustered together, so they're not quite as linear. Now, a line of fit is a straight line that best mirrors the pattern of the scatter plot and can be used to make predictions about the data. So, for example, in our strong positive, I can draw a line that approximates the general direction and path of the data. Same with our negative, but if we have no correlation, we have no line of fit. So first we want to be able to identify strong, weak, positive, negative, and no correlation. So here I have a few examples. In our first example, as you can see, we are generally moving upward, so we're positive. In our second example, we're generally moving downward. In our third, we're generally moving downward. In our fourth example, there's kind of everywhere. In example 5, we're moving downward, and in example 6, we're moving upward. And as you can see, example 5 and example 6 are more closely clustered together. So example 5 would be a strong negative. And example 6 would be a strong positive. Now examples 1, 2, and 3 do show a positive or negative trend, but it's not quite as clustered together. So we would say this was a weak positive and a weak negative and another weak negative. Now example 4, as you can see, the points are just sort of scattered randomly. So example 4 would show no correlation. right, so we want to use data that's been given to us to make a scatter plot. So first we want to look at this, and we've got fat grams and calories, and we have different types of food. On our graph, we've got calories on our y-axis and fat grams on our x-axis, and we want to just randomly start, not randomly, but in order putting the points. 3 fat grams, 50 calories. So 3 is halfway between 2 and 4, and here's 50. 9 is halfway between 8 and 10, and the shrimp have 9 fat grams and 190 calories. Now, I have 150 and 200. So 190 is going to be just under the 200 line. 7, which is halfway between 6 and 8, is 170, which will be a little lower than 190. 10 is 185, which will be almost even to 190. 7 again is 165, which is pretty much right on top of the 170. And then 19 is 245, which is just below our 250 line. Now this shows a positive correlation. Let's try another example. We're going to make a scatter plot, and we're going to describe the correlation. Now we have buildings and city, and then we have stories and height. We have number of stories to go across the bottom and height to go across the y-axis. And I don't have any numbers here, but as we can see, our lowest number is 55 and our highest number is 110. So I have 1, 2, 3, 4, 5, 6, 7 lines. If I were to go up by 5s, we can't fit this here. So I'd go 55, 60, 65, 70, 75, 80, and 85. So I'm going to have to go by 10s. So I'm going to start with 50, 60, 70, 80, 90, 100, and 110. I want to make sure I can fit all of my data. So at 110 stories, the Sears Tower is 442 meters. Well, 450 would be right in the center, so I'm going to go just below the center of 400 and 500. 102 will be not quite, here's 105, so 102 is going to be not quite halfway between there. I have 381 meters, so between 300 and 400. 55 is halfway between 50 and 60 at 312 meters, so just above 300. 75 is 310. 57 is just past the 55 mark, and we're at 290, so just under 300. 76 is at 287. 72 is at 281. 60 is at 265. We can see that it is almost horizontal, but it has a general positive correlation, so we'll call it positive, because it's not a no correlation, and it's definitely not negative. We just sweep up slightly. Okay, we're going to make a scatter plot, and then we're going to draw a line of best fit and use the data to predict American homeowners in 1955. So we have year and percent. Time is always an x-axis. And then we have percent on the y-axis. I have 1950 to 1990, so 40 years. So if I make this 50, 60, 70, 80, and 90. And then percent-wise, I go between 55 and 64. So if I start at 55, I can make each line 1%. And I have room. Now in 1950 we were at 55%. In 1960 we were at 61.9%. So here's our line for 61. 0.9 is almost to 62. 1970 is at 62.9, so almost to 63. 1980 is at 64.4, which is almost halfway. And 1990 comes down a little bit. I guess I should have put the 65 up there. Okay, now we have to draw the line of best fit, and we want to draw a line that best mirrors the pattern of the data. And we want to try to get an equal sort of spacing on either side of the line with our points. So if I come along and I cut up through here, to me this line is the best fit for the data. Now, your line of best fit and my line of best fit may not be exact, but you get as close as an approximation as you can. It's less of a science and more of an art. You're trying to draw a straight line to represent not straight data points. I realize my line is not straight, but we'll pretend it is. Okay, so here's my line of fit, and I want to see how many homeowners were, what was the percentage of homeowners in 1955? Well, 1955 would be right here. So I'm looking for this point here, and it's between 56 and 57. And it's close to halfway, so I'm going to go ahead and say 56.5%. This is my best guess based on the line that I drew. Okay, in this example, we are going to do a little bit more work. We've got some points to plot. The first thing we need to do is find missing data, and then the second thing we're going to do is estimate the amount of rainfall in the year 2015. Now, in our previous example, we were estimating data inside our data points. And we'll be doing that again when we find the missing data. However, on the second part where we estimate the rainfall in 2015, that is outside of the data point, so that's going to take a little bit more work. So the first thing we need to do is create our scale. Along the bottom we'll do the year, and along the side we'll do the millimeters. We'll start with 1990, 91, 92, 93, 94, 95, 96, 97, 98, 99, 2000. And then our smallest amount of rainfall is 12, and our largest amount of rainfall is 42. I don't have enough lines here to make each of these 1, so I'm going to go up by 2s, and I'm going to start with 10, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, and then 46, just to give us a nice spread. In 1990, we had 18 millimeters of rain, so that's our first data point. In 1991, we had 21, so that's halfway between 20 and 22. 1992 is missing. This is some of our missing data, so we need to find 1992. Okay, in 1993, we have 28 millimeters, so that's this point right here. In 1994, we have 31, so that's halfway between 30 and 32. 95, we have 33. 96, we have 37. 97, we have 12. So we'll come back down here. 98 missing. 1999, we have 40 millimeters. in 2000, we have 42. Now, this data point right here would be kind of an outlier. We're not going to use that when we're trying to estimate our line of fit. We're going to use our data that shows a strong positive correlation, and we're going to draw a line that we feel best mirrors the pattern of the data. So we draw that line. And of course, if I was doing this on a piece of paper, I would make sure my line was really straight. Now for 1992, our missing data, we'll come to 92, and we're going to move up along, and we're crossing right here at 24 millimeters. So that's my best guess for 92. 1998, we're coming up to this point, and we're talking about 40 millimeters. Now, we found our missing data. Now we need to estimate the amount of rainfall in the year 2015. So the first step for this is to find the equation of the line. Right? Now I need to find the slope to find the equation. So we need to find the slope. And I have 2 points that are directly on the line that were perfect points. And so I can count from here to here, and I can find my slope. So I'll go up 1, 2, 3, 4, 5, 6, 7, 8. So I go up 8. And then I go over 1, 2, 3, 4, 5, 6, over 6. So my slope is 8 over 6, which is 4/3. Then I plug that in to y equals mx plus b, and I solve for b. Now I can pick either of these points as my x and y. Because I have 4/3, I'm going to pick, now neither of these divide evenly by 3. So I guess it doesn't matter. So I'm just going to say that 24 millimeters is equal to 4/3 of 92 plus b. Okay. Should probably make that 1992 just to be safe. So 24 is equal to, so I need to do 4/3 of 1992. So I'm going to take 1992 and I'm going to multiply it by 4, and I'm going to get 7,968 thirds plus b. Now if I divide that by 3, oh, it does divide by 3. That's awesome. Okay, so 24 is equal to 2, 6, 5, 8 plus b. Okay, so I need to use, okay, so I'm going to use the year 1992 and 24 millimeters. Now 24 millimeters is equal to 4/3 of 92 plus b. Now 4/3 of 92, I'm going to do 4 times 92. So I'm going to get 24 is equal to 368 thirds plus b. And I will get 24 is equal to 122.7 plus b. Now I did round that. I'll subtract 122.7 from both sides. And I get b is equal to negative 98.7. Now, this would be my y-intercept, which would occur in the year 0, and obviously there were not negative 98.7 inches or millimeters of rain in the year 0, but we can't be 100% accurate with this. So, once I found that, the last thing I need to do is I need to make the equation. So I have y is equal to 4/3 x minus 98.7. And I want the year 2015. Now I used 92 for 1992. So that's going to be 8 more years to 2000 plus another 15 years. So I'm going to do 92 plus 8 plus 15 to figure out what number to plug in for B. So 92 plus 8 plus 15 is 115. So I'll do 4/3 of 115 minus 98.7. 115 times 4 divided by 3 is 153.3 minus 98.7. Okay, so if this trend continued, in the year 2015, we would have 54.6 millimeters of rain.